in part E of module 3, linear recurrence relation. Why we need to do this? The reason is very simple, because the question, how do we discover the Fibonacci formula? Last time we verify it, but when we verify it, someone needs to find it for us, okay? Yeah. So we bypass the discovery step. Yeah. But in the real world, when you need to find a brand new formula, so nobody knows it before, so you have to discover it. Yeah. Here, this last topic, we will learn a systematic method to solve that linear recurrence relation. Yeah. This topic you have learned in discrete math, but here I just go through it another time. Yeah. So I hope in this time you can completely master this method. Yeah, very basic. Yeah. So let's start. First, let's look at the problem first. Yeah. First, let's try to understand the official name of this recurrence relation. Yeah. Yeah. Look at this recurrence relation. Yeah. A very simple one, but there is an official name for it. So what is that official name? Yeah. Look at this long name. Second order linear homogeneous recurrence relation with constant coefficients. So long. Yeah. This long. Okay. Yeah. Second order linear homogeneous recurrence relation with constant coefficients. Let me explain why it has such a long name. First, it's a second order. So why second order, not first order? Yeah. Second order, look at the right-hand side. There are two terms. Two non-constant term. Two non-constant term, right? Yeah, yeah. The second order, yeah. If we need to compare, in order to understand the second order meaning, we may like to compare with our old example. Yeah. Remember, in the old example, there is we learned one called that Tower of Hanoi. Remember that problem, that puzzle? Yeah. In that one, we derived, yeah. Oh, just a minute. That one derived that. Probably I skipped that. Yeah. Yeah. So later sometime I will bring it back. Yeah, because in that Tower of Hanoi, we have a simpler recurrence relation. So that is Cn equals 2Cn minus 1 plus 1. Okay, so here you can see at the right-hand side, there is only one non-constant term. And for this type, we call the first order. Okay, yeah. Here, right-hand side, we have two non-constant terms. So we call the second order for its name. Okay, yeah. Linear, yeah, to understand the linear, so you can see each term is a linear term. No square, no, so the exponent. So each term, the exponent is 1. Each exponent of each term is 1. exponent of each term is 1. So that's the linear term. Yeah. So that's the reason we call it linear equation. Yeah. They're homogeneous, this name. Why the homogeneous? Homogeneous, yeah. Look at this. Look at Tower of Hanoi example. Look at this +1 thing. +1, it's a constant. It's a non-zero constant there. Yeah. So this is non-homogeneous. Non-homo. Yeah, let me just write this. And look at here, the constant part, 0 constant. Yeah. For an equation, when the constant part is 0, we call it a homogeneous equation. Yeah, that's the name. So this one, we have that property, homogeneous property. Yeah. Recurrence relation with constant coefficient. So what do you mean constant coefficient? Look at the coefficient of each term. The first term is 1, it's constant. The coefficient of second term, also 1, also constant. Yeah. Because sometimes you may have a non-constant efficient. For example, n minus 1 fn plus n plus 1 fn minus 1. How about that? N plus 1. Okay? That is non-constant coefficient. Yeah, if you compare with that. But here, both coefficients are 1. So in order to cover all the properties for this type of equations, so we give this long name. Yeah, let me repeat it the last time. So that is the second order linear homogeneous recurrence relation with constant coefficients. Yeah. All right. Next, we need to solve it. Yeah. We need to use a systematic procedure to solve it. Yeah. Standard procedure. Yeah. All right. And we consider a general case, yeah. Not just this special example. Yeah. The general. Yeah. The general case, A sub k equals capital A constant capital A times A sub k minus 1 plus B times A sub k minus 2, with B not equal to 0. Because if B equals 0, then it becomes first order, not second order. Here, we only want to consider the second order. First order, much easier. So we do not worry about the first order. Yeah. Yeah. All right. And for the Fibonacci case, A, capital A and the capital B both equals 1. Yeah. So you can see that's the simplest case. Yeah. All right. Now, so let's go through the procedure solving this problem. All right. Before I run this procedure, I want to give you some inspiration. So why we choose this method? There is some good reason behind it. Yeah. So let's take a special view. Yeah. We try to find some rationale behind this procedure. Yeah. Consider a sequence. Here, let us consider the little a sequence. All right. And we like to guess some special pattern for this little a. Special pattern, guess. Yeah. In problem solving, guessing is very important. Yeah. Guessing, we try to, predict. Yeah. Guessing actually making prediction, right? Yeah. The guessing step is the prediction step. Yeah. When you make a good prediction, then you can solve the problem easier. If you cannot make good prediction, then it is much harder. Here, we want to make some good prediction. But for the pattern, so we may feel how, because when you make a guess, your guess has to come from some related information, right? Yeah. Because you cannot make baseless guess. So you have to provide some, evidence or some, based on some existing information, then you make some reasonable guess. Yeah. Here, we need to have that part. Yeah. When we guess a pattern, we need to find some good reason behind that pattern. Yeah. All right. So here, the pattern structure, we guess little a sequence should take this t to the k power function structure. Yeah. So this is a power function structure. Yeah. Okay. But you may wonder, so why, how do you know you should take the power function structure? Yeah. Here, let me give you the reason. Yeah. Look at the first order case. The first order case, Cn equals A times Cn minus 1. Okay, let me omit the constant term. Yeah, we consider the homogeneous case. How about that? Yeah. Look at that. To solve this recurrence relation, very easy, right? Because the obvious solution, Cn, because you just do iteration, you can get equals a to the n. Yeah. Because from Cn minus 1, you can get Cn minus 2, right? You can get a squared Cn minus 2, and so on. Keep doing that, and at the end, you get Cn equals a to the nth. Right. That is the power function, right? That is the power function. So you can see the solution structure for the first order linear recurrence relation, homogeneous recurrence relation. That's the power function, the solution structure. Yeah. Now, when we move to second order, can we borrow? Can we try the same structure here again, another time, right? Yeah. That's the, base information for our guess, right? Yeah. Yeah. So it's not baseless. So that's the base of our guess. Okay. The rationale. Yeah. Some good reason, reasonable reason for this structure. Okay. Yeah. So we take this power function, t to the nth. Yeah. T, what is the t? Yeah. You may argue, what is the t, right? T, unknown, and to be determined. How about that? To be determined. Here we do not know its value. Okay, to be determined. Yeah, we will figure it out. Yeah. All right. And we know the structure people also call geometric sequence, arithmetic sequence, and a geometric sequence. Yeah, but it is just a name. Okay, yeah. But now let us determine the t value. Yeah. But when we determine t value, we, for simplicity reason, we can ignore the initial condition. Yeah, yeah, because to avoid any complexity, yeah, so we just want to make our current problem as simple as possible. Yeah. So let's just ignore the initial condition. We only want to consider a solution for that recurrence, original recurrence relation. So let's plug in. Yeah. Let us determine that little t to give us just one solution, simple solution for the original recurrence relation. Yeah. So let's plug in left-hand side, AK, based on our assumption, it should be t to the kth. Yeah. Similarly, a to the a sub k minus 1, t to the k minus 1, and so on. All right? Yeah. Just solving this simple equation. That should not be too hard, right? Yeah, because only one variable, t. Yeah. So this equation, we should be able to solve it. Yeah. But the exponent part, not that easy. K unknown. Yeah. Can we simplify it? Can we make this equation as simple as possible by cancellation? We can do some cancellation. Yeah. All right. After cancellation, yeah, actually we do division by the lowest power of t to the k minus 2. Yeah. Do this division, both sides. Then you will get a very simple, we call quadratic equation, right? T squared equals t plus 1. Quadratic, simple quadratic equation. And in this equation, we're familiar with this equation. Look at that. So if we write it to the standard quadratic equation, you can see this t squared minus t minus 1 equals 0. We're familiar with it. Yeah, that's because we solved this equation before, remember? When we try to find the golden ratio, that is this equation, is x squared minus x minus 1. X is the golden ratio. Exactly the same equation, right? Yeah, just the variable, we use different variable. That's not important, okay? Using x or t, yeah, that's not very important, just a variable, okay? Then the solution should be, or at least the same way to find the solution. Yeah, because we have the quadratic formula. When we apply the quadratic formula, we can find two solutions. T1, the golden ratio, the familiar golden ratio expression, 1 plus root 5, whole thing over 2. Yeah. T2, 1 minus the conjugate solution, that one, 1 minus root 5, whole thing over 2. Yeah. So you can see we find two different solutions for the current quadratic equation. Yeah. Actually, we found the same two solutions when we try to find golden ratio. And because the definition of the golden ratio, so it's a ratio of the length of two line segments. We know it must be positive. So we drop the negative solution. Yeah, so that's the, golden ratio story. Yeah. But here, this little t, what's the meaning of this little t? The meaning of this little t, just one solution for the, that gives us a solution for the current recurrence relation. It has nothing to do with the golden ratio, right? From the definition, it has nothing, we do not interpret it as the golden ratio. Okay. And we do not have to connect it with the golden ratio, right? Yeah. Yeah. So that means the negative second solution should not be dropped. We should keep the second negative solution. Yeah, because we do not assume this T is the golden ratio. There is no reason that T cannot be negative number, right? Yeah. So that means these two solutions should be considered as valid solutions for the given recurrence relation. That's the conclusion. The conclusion is we find two different special solutions for the given recurrence relation. One, T1 to the kth, and second, T2 to the kth. Yeah. All right. So that's our first step. Second step. Yeah. Because that's two special solutions, right? Two special solutions. Now we want to consider initial condition. Yeah. Because for those two special solutions, we didn't consider the initial condition for the recurrence relation. That's not good. That means those two solutions won't be our final solution, right? Because definitely T1, T2, they're non-integers, right? T1 not integer, T2 not integer. When you raise to the kth power, still they are non-integers. That cannot be our Fibonacci numbers. Yeah. So our next thing is we need to really find a solution that satisfies the given initial condition. Because only when you satisfy the initial condition, then you can get Fibonacci numbers. Yeah. So we need to bridge that gap. Still, there is a gap there. Yeah. But we need to do some work to bridge that gap. Yeah. So let's see how do we complete that last mile. Okay. All right. So let's start with this one. Yeah. Yeah. So two solutions. These two solutions, we can make two special solutions for the given recurrence relation. Yeah. So that means if you plug in T1 into the given recurrence relation, you have that. So no problem, because we solve the equation from there. So now we plug in back, it must be correct. Okay. The second T2, if we plug in, we also have this identity, these two identities, okay, or equalities, correct equalities. Yeah. All right. The question, yeah, the next step we need to do, we need to find a new solution that satisfies the given initial condition. New solution. But this time we need to factor in the initial condition. Yeah. The question, how do we do it? Okay, yeah. With two special solutions, how do you make a new solution from two non-special solutions? That's our current question. Okay, yes. So to answer that question, we need to use some special technique in math. Yeah, special technique in math. Yeah. All right. Yeah. Yeah. So now, so consider our goal. Construct, let me write our new goal. Okay. Yeah. New goal, okay? Construct a new solution from two special solutions. That's our current goal, okay? Yeah. The question, how? How to do that construction, okay? Yeah, all right. The construction, so here, there is a simple idea in math, very simple, yeah. But if I do not show you this simple property, it's hard to imagine the simple construction way. Yeah, the construction is very simple. Yeah, all right. So let me go there. Yeah, the question, how to use two special solutions without the initial condition to get a new solution with the initial condition. Yeah, so that's what we are going to do. Yeah, we need to take advantage of one special property of the given recurrence relation. One special property. Remember, at the beginning, I gave you the long name of the recurrence relation. Yeah. One of the properties, because that long name covers several properties of this equation. Here, we just want to take advantage of one of the properties there. Yeah. So let me repeat that name again, long name. Second order linear homogeneous recurrence relation with constant coefficients. All right. In that long name, there is one word called linear. Linear. This property is useful here. Here, we just take advantage of this useful property. Linear, that gives us the property called the linearity property. Linearity property. We want to take advantage of the linearity property. Okay? Yeah. To do the construction. Yeah. So here, construct. Do this construction. Okay? Take advantage of the linearity property. Yeah. How? Yeah. So let's do next. Taking advantage of the linearity property, we can combine two solutions in a special way, and this way is from the linearity property. Look at that, okay? Yeah. All right, so now the combination. All right. The combination, there is a name for it called a linear combination. How about that? Linear combination of two variables, x and y. Yeah. In math, we frequently do this kind of combination called a linear combination. When we need to make a new expression from two variables, x and y, and using the linear combination, we mean the expression is capital AX plus BY. Capital A, capital B, both constant. Okay, AX plus BY, this expression is called the linear combination of X and Y. Here we take advantage, or we just use this way to combine two solutions, two existing solutions. Yeah. Yeah. All right. Yeah. So here you get an idea. Yeah. Why? Yeah. So you may ask, why you use this special linear combination to form a new solution? Because you will see in this way here, capital A unknown, capital B unknown. So any constant A any constant b, if we put it here, we do this linear combination, we will get a new solution. Look at this conclusion. So let me say in this way. Linear combination, capital A, T1 to the kth plus capital B, T2 to the kth will be a new solution for any A and B. Can you see that? Can you see this nice thing? Yeah. The reason behind it, why we get for any capital A, any capital B, we do this linear combination, because if you plug in our original recurrence relation, by the linearity property, this must be a new solution. That's the reason the linearity property is important for this equation. I can show you, this linearity property, I can show you why it is correct. Okay, any linear combination of two solutions is also a solution. Why it is correct. Okay, here we use this property, so this is a property, but you may ask me why it is correct, right? All right. Let me explain a little bit here. All right. Let me use little room here. T1 to the k, that is a solution, right? Equals T1 to the k minus 1 plus T1 to the k minus 2. The first solution. T2 to the kth, the second solution, T2 to the kth, and second solution. Can you multiply the first equation by A, you multiply second equation by B, and adding them together? You can do that, right? First equation, both sides you multiply by A, and the second equation you multiply both sides by B. So you get two equalities, right? So both must be correct. Okay? Two correct equalities. Then you add them up. The new equality must also hold. Okay? That tells you this A T1 to the kth plus B T2 to the kth, it must be a new solution after you add them up. And this only true when the equation is a linear equation. If it's non-linear equation, you cannot do this. Okay? Even if you do this way, you won't get a new solution. Okay? So only the linearity property can preserve that solution property. Okay, all right. So next, we know our new solution takes this form, but capital A, capital B, undetermined. We need to determine capital A and the capital B. So the last thing we need to do, we need to plug in some number, plug in for two cases, base case, n equals 0 and n equals 1, because these two corresponds to the two base cases. So we use the two base cases, we can determine capital A and capital B. So that's the last thing we need to do here. Okay, two initial conditions. So the last step pretty straightforward. So we just plug in and solve the equation, determine coefficients A and B. All right. where n equals 0, yeah. So let's plug in n0 into this formula. After simplification, we get a plus b equals 0. Yeah. So b must be negative a from the first equation. The second one, you're plugging n equals 1, you get a1 equals this expression. After simplification, we know its value is 1, the base case, our second base case. Yeah. So after you simplify this equation, but at the same time use b equals negative a. Yeah, so you replace b by negative a and do some simplification, you will get a times root 5 equals 1. So a equals 1 over root 5. Yeah. And the b equals negative 1 over root 5. Then you replace. Now we determine the values for a and b, so you can put them back to the original formula. So we get our Fibonacci number formula, and we know to write the formula, this time we can replace that 1 plus root 5 over 2, the golden ratio expression phi. So, and 1 minus root 5, yeah, over 2, we know the reciprocal way, so it equals negative 1 over phi. Yeah. So finally, the final expression is 1 over root 5 parenthesis phi to the n minus negative 1 to the n over phi to the n. Yeah. Okay. That's the whole discovery procedure. All right? Yeah. Here, yeah, because I give you a long story to describe why we choose that pattern, geometric sequence pattern. Yeah. Yeah. But if you understand this whole story, when you need to solve a problem, so you can just, work on the equation directly, characteristic equation. Yeah. So there is a name, characteristic equation. Yeah. So you solve, yeah, because people, when they do it, the first step, you start by solve the characteristic equation. For the given recurrence relation, that is, yeah, you can use x. Now, you do not have to use t. Okay, yeah. Characteristic equation from there, yeah, because x squared equals x plus 1. That's the characteristic equation. When you start, you solve this equation. So you have two solutions. Then you use a linear combination, x1 to the nth plus b times x2 to the nth, for your general solution. Then you determine a and b from the initial condition. Okay, determine. The standard way. Yeah. So this is the standard way. Okay. Yeah. All right. So we'll complete this topic. Yeah. All right. So try to understand. Yeah. So I'll give you a long story to help you. Yeah, because we want to understand what's going on. Yeah, behind the special method. Why we do it this way? Yeah, there is some good reason behind it. Yeah. All right. Yeah. So we complete whole module 3. Yeah.